Okay, you may not be quite as familiar with the concept of acceleration as with velocity, so let's just go through and show the similarities and differences here. Velocity is defined as the rate of change of position. So S is a symbol we use for displacement, and how far you move per unit time is going to be your velocity. And this is a vector, and so that's a vector, okay? By the way, S is a sort of what's used as a generic position variable. X, Y, and Z are used primarily to refer to the coordinate axes, although frequently in one-dimensional problems we just call it X instead of S. But it's quite common to use S for displacement. Acceleration is the rate of change of velocity. It's the change in your velocity per unit time. Okay, so there's a definite parallel construction here. And again, the delta refers to the final value minus the initial value. So your velocity is where you end up minus where you start, and that distance is divided by time. Here is the final velocity minus the initial velocity over time. So whenever it's convenient, you can replace the delta with the actual difference. Okay, if you look at the definition of acceleration, delta v over delta t, look what happens on a graph of velocity versus time. Notice that delta v would be a measurement in this direction, and delta t is a measurement in this direction. And so this looks a lot like a slope. So let's put a slope here at a particular point. So at this point on the graph of velocity versus time, the tangent line would be like this. And if I take delta v and delta t, there's supposed to be straight lines there, that gives you the slope. So over here, notice the slope is steep, so it's a large acceleration. Here it's getting smaller. Here it's perhaps briefly negative. Here it's 0, and here it goes positive again. Okay, so acceleration can be interpreted graphically as the slope of the tangent line on a v versus t graph, very much like speed or velocity was the slope of the tangent line on a position versus time graph. Let's look at a concrete example. Okay, we're going to look at some motion graphically here. And so here I'm actually generating some data, and we're going to plot it over here. The graph is going to show how it's going to move. Y is the vertical position, and that's versus time. So Y versus T is the up and down motion compared to time. The coordinate axes I put on here, so down here is the origin. So we're starting at some positive height. Then we're going to toss it up. It's going to go through a maximum and come back down, as you might anticipate. Here's the motion, and there's the graph. Okay, so let's look at this graph in the data tool. So we have the height as a function of time. We already have the curve fit option turned on. I'm going to fit a parabola to it. If I pull this down, you can't see it, so let me move this up a minute. Okay, here's the pull down, and there it says parabola. Let's try a parabola for this curve. Bring this back down. Okay, and notice if I choose a chunk of data near the top of the curve here, I'm fitting a parabola to these points, and that same parabola fits all of these points along the path very nicely. It's a little bit off at the end where air resistance gets larger because I'm moving faster through the air, and it doesn't fit at all up here when my hand is in contact with the ball. So it looks like we're going to get a parabolic graph when we have something moving under the influence of gravity alone. Now, we've seen already that if I take the slope of this graph everywhere along the line, it'll give me the velocity. I could do that with the data table. We can also let tracker do that, and so I'm going to do that by saying v sub y. So what we've done is tracker's calculated the velocities everywhere along this motion. Let's go back to the beginning. I'm just going to step through it, and notice that as I'm pushing it upward, right about here is where I'm letting go, and notice as soon as I let go, it gets onto this straight line portion of the graph here, okay? And so it's moving upward at about 2 meters per second, it says here. And as I continue, now it's moving upward about 1 meter per second, And now it says 0, and notice that it's right at the top of its motion. And then it goes from 0 to negative, and here's about -1, -2, -3, -4, and so forth. Okay, so it looks straight line even though I went up and over the top. I didn't have to do a separate upward portion and a downward portion. It's just one continuous motion where I'm going from larger velocities to smaller velocities right through 0. Let's look at this in the data tool. Right click, analyze, and let's see, that says parabola still. And again, I can just barely, maybe you can see it says line at the bottom. I'll just pick it anyway. And so it's going to fit a best straight line to whatever data points we choose. Let's go from about here, about there. And I'm staying away from these points and these at the end. And notice down here is the equation of the line, and the slope of the line is A, and over here it shows what A is, minus 9.8, and that's going to be characteristic of things that are falling under the influence of gravity. And notice I said falling even though I'm throwing it upward. As soon as I let go, it goes into free fall. In other words, it's moving under the influence of gravity alone. So it doesn't matter if it's moving up or down, or momentarily even at rest, it's moving under the influence of gravity, and it's constantly going to be changing the velocity in a downward direction with a nice straight slope there. That's interesting. Okay, let's use that concrete example as a model, and notice the pattern we have when we try these three different kinds of graphs. What if I start with position versus time, or displacement versus time? Now in the example we used y, but it's the same thing here. It doesn't really matter what letter you use. Here we have velocity versus time. We didn't do the actual graph, but we saw from here we had a constant acceleration versus time, okay? And we see a relationship among these graphs. If I start with our position versus time graph, it turns out in the case of motion under the influence of gravity, it was a parabola, and we actually fit a parabola to it, and it came out very good. We're going to see later on the reason why it is a parabola, but we'll come back to that. Notice that from this graph, we can derive a second graph by simply taking the slope at every point along the way. We come up with the velocity as a function of time. So here the velocity is positive, here it's 0, here it's negative and increasingly negative, and we can see it's positive, 0, negative, increasingly negative right here. And so it turns out that the slope of a position versus time graph gives us our velocity versus time. And if we start with this parabolic trajectory here, our velocity graph is going to be a straight line. We can do a similar kind of process then, taking all these points along the velocity graph and finding the slope. And by the way, since it's a straight line, the slope is the same everywhere. And so in this case that we did, the slope is negative everywhere. So we can derive another graph, which is acceleration versus time. We didn't actually show the graph, but you can see what it would be. And here's our constant acceleration. So it's just a horizontal line indicates that the acceleration is constant. And it's negative because this is a downward slope. Okay, so this is going to be the pattern, so that if acceleration is constant, whether it's negative in this case or if it's positive, the velocity time graph will be a straight line with some slope equaling whatever the height of this graph is. The height here translates to the slope here. The height here translates to the slope here. Okay, we're going to come up with a set of equations, and it's common, I think, for people to misapply these equations to just any kind of motion. The equations that we're going to derive are going to apply to motion where the acceleration is a constant. And if you want a more general kind of analysis where the acceleration could be anything whatsoever, come back and take a calculus-based physics class, because that's what that's all about. So really, calculus was invented in order to do physics. We can do a limited subset of our problems just algebraically here if we limit ourselves in certain ways. So we're going to limit ourselves to constant acceleration problems. Okay, here is a similar kind of a graph. And what I'm going to do here, notice the acceleration in this case is positive. So maybe you're in a car and you're taking off from a stoplight, and as you move down the street, you're accelerating, for a limited period of time. You can't go on forever like this, of course. Okay, so here is our equation for acceleration in relation to velocity. The question is, if you know this graph, can you figure out your velocity as a function of time? Okay, well, look at the definition. Acceleration is delta v over delta t. If I bring that delta t up there, we get this equation. Delta v is a times delta t. Okay, well, what does a times delta t look like graphically? Well, a is just the height of this graph right here. It's the height of this function. It's the value of the function here. A is a function of time. And delta t is how much time has elapsed from when we started to some point. So let's say this is delta t, all right? And here's our final t, and here's our starting point, all right? Notice that if I take this times this, that's the same as the area of a rectangle. Height times length gives you the area. So here's your height, and there's your length of this rectangle. So the area here is going to be the velocity. It's going to be the change in velocity, excuse me. So there's some starting velocity, might be zero, might not be zero. But the change in velocity is going to be given by the area under this graph. So if I want to find my velocity as a function of time, I could say my final velocity minus the initial velocity, which is my delta v, is equal to a times delta t. And so if I say, what's my final velocity, I can say that's equal to v naught plus a delta t. And there you have it. Here is your velocity as a function of time. Okay, so that's the first step. We're starting from the assumption of a constant acceleration, and we found what is the velocity as a function of time. Our initial velocity is something we have to just state. We can't derive that, but let's say that we know that we have a constant acceleration problem, and we know the initial velocity. We can find any other velocity as a function of time. So just summarizing, starting from the definition of acceleration, we can get the delta v is equal to a delta t. We can split up the delta v into the final minus the initial, solve for the final velocity, and the final velocity is v naught plus a delta t. Now, let's do it again, except this time we're taking velocity as a function of time, and I'm not on the same problem anymore. I'm taking a special case where the velocity is a constant. So this goes back to your Algebra 1 problems. If you had a constant velocity, this is how you could find the displacement or your position, okay? Now I'm doing this just to illustrate the math. We're going to get back to our constant acceleration problem in a minute. But let's look at the case where we just have a constant velocity. Notice that the same algebra applies, except the names have changed. And so if I solve for delta s, it's v delta t, okay? And v is the height of this graph, and delta t is the length of this rectangle. And so the one times the other is simply the area. And so here's the area under the graph of velocity versus time, and that's going to give us our change in displacement. That's going to give us how much we've moved. Okay, here's a more general case where the velocity is not constant, but in this case it's varying linearly. The argument here is going to apply whether it's a linear function or not. Any kind of a graph of velocity versus time, you could apply the same reasoning to. But remember, we're limiting ourselves to constant acceleration, so the slope of this graph has to stay constant. Notice if I take a very thin slice of this, a little tiny strip here, I have what could be thought of as a little rectangle. And if I want to get better approximation, I go thinner. There's a little variation here, but that doesn't change the area under the graph by very much. And so if I squeeze this until it's as thin as we needed to get as much precision as we want, we can say the area under a little strip like this would be the distance that you've traveled. This is the delta s, okay? So there's your v delta t, this is your v, and this is a tiny little delta t. So how does this apply when we want to make a larger movement? Well, you could add up all the little strips, okay? And so that's like finding the area under the entire graph. And if I think of this area, even though it looks here like it's a trapezoid, but it still could be thought of as like an infinite number of infinitesimally thin strips, the meaning is that the sum of all these little strip areas equals the area under this overall graph. So the area under the graph of velocity versus time is going to be the delta S. It's going to be the distance traveled, regardless of whether this is a constant or a straight line or actually any other kind of a curve. We're going to do our equations based on the idea that this is a straight line here. So how do we find what this area is? Well, this point is our initial velocity. That's where we started out. And then the final velocity is whatever point we want to stop the clock. That velocity, the final velocity, is v0 plus at, because we came across this equation earlier. That's, again, that's just from the definition of acceleration. So we have what we need to find the area under this trapezoid. The formula for the area of a trapezoid is the average of the bases times the height. So that's like saying if you knew the height here, you could just take the average of these two parallel sides. The bases are the parallel sides. And so that's like putting this area down here and make a rectangle out of it, right? So the average of the bases times the height, in this case it's on its side, so the height is sideways. So it's going to be the average of these heights times this gap here. Well, how do I average these? Well, I add them together and divide by 2. So let's do that. So let's take the final velocity, which is v0 plus a delta t, add it to the initial velocity, so we'll just make it 2v0 plus a delta t, and divide by 2. Multiply that by the height, which in this case is the sideways distance here, which is delta t. Okay, and that'll give us the area, which is our delta S. Okay, let's simplify this a bit. Divide both of these terms by 2. I get v0 plus 1/2 a delta t. All of that is times delta t. If I multiply in the delta t, I have v0 delta t plus 1/2 a delta t squared, and that gives us delta S. Okay. If I split up my delta S into final minus initial, I'm going to rewrite it under here. Take SF minus S naught. Okay. And if I bring the S naught to the other side, the final position, I'm turning it around, is equal to S naught, initial position, plus V naught delta t, plus 1/2 a delta t squared. So we now have an equation for where we are. We did this in 2 steps. The first case we found from the constant acceleration, we found what the velocity is at any time. And from the velocity graph, we found what the position is at any time. So let's come back to this little summary page that we did earlier, showing the 3 kinds of graphs. Position is a function of time, velocity is a function of time, and acceleration is a function of time. We know that we can go from one graph to the next if I'm going up this way, up the chain, by taking the slope at every point. What we've now seen is you can come back the other way by finding the area. Okay, so it looks like finding the slope of a graph and finding the area under the graph, this is acting like this is a set of inverse operations. And by the way, when you get to calculus, this is what calculus is all about. We have a pair of operations. Finding the slope everywhere along a graph is called finding the derivative. And the process is called differentiation. And finding the area under the graph is finding the integral. And so finding the integral is finding the area. it sort of makes sense not to call it area, because area should have units of meters squared or something like that, square feet, whatever. But here the area under this kind of graph is a velocity, and the area under this kind of a graph is a displacement or position. So these areas, so to speak, are abstractly, we found them using area formulas, but what we're actually doing is something that's a little different than actual areas. So finding the integral is a more general way to talk about finding these areas. Finding the derivative is finding these slopes. So I'm just giving you the terminology. I'm not going to teach you calculus in this course. This is a non-calculus physics course. But one of the things about physics is it shows you where calculus comes from. This is the kind of stuff that calculus was invented in order to be able to do in more generality. Here we're limiting ourselves to constant acceleration, and therefore the integral of that comes out a nice straight line, and we can find the area under a straight line because that's just geometry. We can work our way down the line, and finding slopes we can work our way up the line. Okay. In a calculus-based physics course, you can take any kind of an acceleration graph and find the corresponding velocity and position graphs using the same logic, but a lot different kind of techniques in order to find those areas under the graph and so forth. So far, if we start with constant acceleration, emphasis, constant acceleration, and you know the initial velocity, and down here you know the initial position, and you know how much time has passed, you can find the velocity and the distance traveled. Notice one more thing about these equations. We started with the assumption the acceleration is constant, and under that assumption we came up with an equation for velocity that's a linear equation. This is the equation of a straight line. And also the equation for position as a function of time is quadratic. This is going to be a parabola, and this explains why it's a parabola. We saw experimentally that when you throw a ball into the air, the height, when graphed as a function of time, comes out a parabola, but this shows why that's true. So, constant acceleration, linear velocity, and parabolic position is characteristic of the kind of problems we're solving at this point. It turns out you can use these two equations to solve pretty much any constant acceleration problem out there. But there's one other equation that is frequently going to be very useful, so let's derive it right now as well, just algebraically. So let's take the two equations we just found, and we're going to eliminate delta t between them. Sometimes you don't know how much time has passed. Sometimes you might just know how far you've gone. How then can you solve the problem? We need time in both of these equations, but maybe you don't know the time. So let's just algebraically eliminate t between these. So take the first equation, solve for delta t. So I have Vf minus V naught divided by A. Vf minus V naught divided by A, that gives us delta t. All right. Now I want to plug this in here and here in the other equation. In fact, I'm going to bring the s's together, it turns out. Sf minus F naught is just going to be delta S is equal to V naught times delta T, which is this expression, plus 1/2 A delta T squared. So this is going to be, let's just square it as we go. This is V sub F squared minus 2 V sub F times V naught plus V naught squared over A squared. And that's it. So we've substituted this into there. So now we no longer have delta T. We just need to simplify. Notice this A cancels one of these. Let's put the 2 down there. And so here we have 2A, and here we have A. So if I multiply top and bottom of this by 2, so let's put a 2 down here, and let's just put a 2 out front. I could put it up there if I wanted. Now we have two fractions to the common denominator. So I have 2A in the denominator. So here I have 2V naught times VF minus v naught plus all this, vf squared minus 2 vf v naught plus v naught squared. All of that's equal to delta S. I'm going to bring the 2a up here. Okay, and let's simplify again. So 2a delta S is equal to 2 v naught vf minus 2 v naught, or 2 v naught squared, plus vf squared, minus 2 v naught vf. I'll write it that way because I wrote it that way over here, and then plus v naught squared. So this term drops out. So here's v naught squared, and here's minus 2 v naught squared. So one of them minus 2 of them is minus 1 of them. So this whole right side becomes vf squared minus v naught squared. I have 2a delta S. Let's rewrite this in terms of our final velocity. Just bring this over and then turn it around. Vf squared equals, bring this over here, it's v naught squared plus 2a delta S. And that's our final equation. Okay, so notice this gives a way to find the final velocity if you know the starting velocity and the acceleration and how far you've gone. There's no reference anywhere in here to how long it has been. So if you don't know the time, that's a hint that this is a useful equation. Okay, here's the summary. We have these two independent equations, and this one is derived from the other two simply by eliminating time. So keep that in mind. These are not three independent equations. We only have two independent equations, and then a rewritten summary that's crunched out of the combination of the other two. Very importantly, notice it's assuming constant acceleration, okay? So for constant acceleration problems, whether it's gravity, whether it's some other kind of source of the acceleration, these are the equations that apply. Don't try applying these when the acceleration is not constant, or it'll give you wrong answers. Okay, so the next video we'll go through some example problems.